So when we talk about vector operations, we're going to talk about addition, subtraction, multiplication with vectors. So to add two vectors, v and w, so the way that would look is v plus w. Draw vector v, and then from the terminal point, that means the endpoint of v, connect it to the initial point of w. The sum of these vectors is the vectors whose initial point coincides with the initial point of v and whose terminal point coincides with the terminal point of w. So for example, if you look at this small image up here, if I'm trying to add two vectors, so if I wanted to add v plus w, you draw v, where v ends, then you're going to, so where the terminal part of v is where you're going to draw w. And then when you connect those two, starting at the initial point of v, going to the terminal point of w, that is the sum of those two vectors. And you're going to see where that comes in to play in a little. We're going to do a quick word problem on it. So the quick question is, does vector addition have the same properties of addition? So let's learn some of the properties of vector addition. So first of all, vector addition, just like regular addition, is commutative. So that is, if v and w are only two vectors, then v plus w equals w plus v. So it's just like 2 plus 3 is the same thing as 3 plus 2. So you can add in different orders and you'll still get the same answer. Vector addition is also associative. So for example, if we have three vectors, u, v, and w, if I first added v plus w and then took that sum and added it to u, I would get the exact same answer as if I did u to v first and then added that sum to w. Additionally, the zero vector, 0, has a property that, just like regular addition, if you add 0 to anything, same thing as if you take 0, add it to the vector, you're going to get, oops, not 0. You're going to end up getting that actual vector. So for example, 0 plus 3 is the same thing as 3 plus 0, which is just 3. And then if v is a vector, then negative v is a vector of the same magnitude, but the opposite direction. So if we were adding v to negative v, so the opposite of it, we would end up getting the 0 vector. And this allows us to write two different vectors, v minus w. So you can see it as, we could rewrite that as vector v minus vector w, or vector v plus a negative vector w. Same kind of deal as 2 minus 3 is the same thing as 2 plus a negative 3. So it's the exact same properties that addition holds on to. All right, let's continue on with vector operations. If alpha is a scalar or a real number, so a scalar would be like if you had like 3 times the vector, so you're multiplying it by a number, and v is a vector, the scalar product is defined as follows. So if that scalar number is greater than 0, the product of alpha times the vector is the vector whose magnitude is alpha times the magnitude of v, and whose direction is the same as v. If alpha is less than 0, the product of alpha times the vector is the vector whose magnitude is alpha times the magnitude of v, and whose direction is the opposite of v. Unless if alpha equals 0, or if the vector is 0, then alpha times the vector is always going to be 0. So for example, use the vectors given to graph each of the following vectors. So if I were to graph v plus w, okay, so we've got v here, so here's your initial, there's the end. Now I'm going to add w to it. So again, when you're adding, you start with the first one. Where that one ends, you put the new one in. So this one is down 2 over 2. So down 2 over 2. So that means our w will go from here to here. So if I was figuring out what v plus w was, it would be starting here, going here. So there's v plus w. If I had to do 2v plus w, so that's going to be taking v and having it done twice and then adding w to it. So let's just do it on here. So there's v plus another v plus a w. And then adding those together. So when you add them together, you start at the initial vector, you end at the last one. So that's 2v plus w. And then the last, if we did this one, so that's going to be v plus 2w minus u. So that means instead of u going up 3 and over 1, u is now going to be going in this direction. So you're going to be going down 3 and over to the left 1. So down over to the left would be about right there. So that would give us, this would be what that answer would be. So that's v plus 2w minus u. So again, the minus u is the same thing as if I would have rewritten this as v plus 2w plus a negative u. So again, the negative, all that does is just change the direction. So instead of it going from here to here, we change that and we're going from that to that point. So that's why this was facing in this direction. Okay, so on the previous slide, hopefully you guys saw in order for us to graph these, we had to look at where it went horizontally and where it went vertically. And we can actually use that to figure out writing these in a component way. So writing a vector as a vector component. When we do that, it makes things so much easier when we're going to add these, subtract these, multiply these, etc. So if based on this, if we're using components to express v, so again, v would be over 3 in the positive direction and up 2, so it's written like that. So based on this, we can express w as, so to get from here to here, we're going over 2 in the positive direction. So you always go from the left point to the right point. And then we're going down 2, so that's going to be a negative 2. So for u, we're going over 1 in the positive direction, and then we're going up 3. So now if we go back and we look at what we did when we added v plus w, and I'll draw it in here just so that we have it on here as well. So when we do that, you can actually see the vector that creates v plus w. Those components would be going over 1, 2, 3, 4, 5, and then up or down 0. Now what's kind of cool is you guys can hopefully see that if I just took this component and I added it to the to v's vector, which is 3, 2. So I took w, added it to v when they're written in component form, add the x parts together and you get 2 plus 3 is 5, and then add the vertical parts together and you're going to get 0. So what's kind of cool is that you can use that method of you basically are adding those horizontal components, those get added together. So v plus w is equivalent to adding 2 plus 3, and then comma, negative 2 plus 2, which gives us 5, 0 for our vector component. So the answer from the previous slide should be yes, we can add those two vectors together. So basically, it can be seen really easily if we position the initial point of the first vector at the origin. So right here. And in that case, that vector is called a position vector. So definition. An algebraic vector is represented as v equals this component, a and b, where a and b are real numbers, called the components of the vector v. If the vector's initial point is at 0, 0, or in other words, the origin, and the terminal point is at AB, then V is called a position vector. A position vector describes a horizontal and vertical movement of the direction of the line from the initial point. So here's another example. Find the position vector of the vector that's created by using these 2 points. So what this means is we're going to start at this point, so that's our initial starting point, so -3, 1. And then it's going to end at P2, which is 6, 3. Okay, so our vector V is the vector that starts at the first point, which is -3, 1, and ends at the second point, which is 6, 3. So I first plotted those points, and we can determine that vector, and then we can determine the actual vector components by this is going over 3 or over 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes up 2.